Good morning. Okay, so let me prepare. Okay, so let's start the class now. We are going to talk about the methods of proving. I believe you have already studied this in the undergraduate discrete math class. So what we are going to do here is to have a very quick review of some of the important techniques that we want you to review. Yeah, because they are going to be used in some of the proofs in the later topics. Of particular importance is the mathematical induction, and also there is proof by contradiction and proof by construction. So today we will focus on the first two, and then we will leave proof by construction for the next time. What is mathematical induction? Okay, so here usually it is used to show a certain statement P of n is true for infinite values of n, and the value of n usually they are from integers. Okay, so this idea is like this. So we want to just show, so our target is to show infinite many values of n will be true. But what we are going to show is, we show these two things. The first one is, we want to show that Pn is true so for some of the particular case where n is equal to k. So we are not going to show for every values of n, but we want to show for some particular value of n, let's say k, P of n will be true. And what is next is, we are going to show that Pn plus 1 is true if Pn is true. Now notice that this is a very different statement than the original one. The original one is just showing Pn is true without any assumption, without any other knowledge. But for here, this part is, we are going to show that Pn plus 1 is true under the condition, under the assumption that Pn is true. So we can safely assume that Pn is true, use this as the information, and then we show that Pn plus 1 is true. So the good thing here is that if we have this assumption, usually we will have extra knowledge, extra information that allows us to show Pn plus 1 to be true more easily. Now, if we have proven these two statements independently, then we can imply that, first of all, the first one is Pn is true for n is equal to k. So we know that Pk is true, right? Now together, in combination with the second one, because we now know that Pk is true, so we have Pk plus 1 is also true. And after that, since we now have Pk plus 1 is already true, we apply this one again, then we know that when Pk plus 1 is true, then we know that Pk plus 2 is also true. So by working with these two statements one by one, we can actually show that Pn is true for all n, starting from k, k plus 1, k plus 2, up to infinity. So we have a couple of examples. I think you can try it out by yourself. So for instance, 1 plus 2 plus 3 up to n, we can show that it is equal to n times n plus 1 over 2. And similarly, we can show that if Fn denotes the nth Fibonacci number, let's say F1 is 1, F2 is 1, and so on and so forth. And what is Fn? Fn is equal to the sum of the previous two terms in general. So F3 is 2, and so on and so forth. Then in that case, we will have F1 squared plus F2 squared up to Fn squared. The summation of all these squared terms will be equal to Fn times Fn plus 1. Now notice that this is a very powerful technique in the sense that once we understand mathematical induction, showing this to be true or showing this to be true is really a piece of cake, very easy. But mathematical induction doesn't give us any, knowledge, extra knowledge. We have to know that this is already true in order to apply mathematical induction. On the other hand, suppose that we start with f1 squared plus f2 squared plus fn squared, and then we have no knowledge, then it is rather hard to know what we are going to show and what is the relationship of this one and this one. So mathematical induction is very useful in checking, in verifying whether a certain relationship is correct. But on the other hand, it doesn't give us knowledge to explain why it is correct. Now we need to be careful. This is a case where we can easily make a mistake. So let's see. We want to show that in a set of n horses, all the horses are of the same color. Now, this is something nonsense because we can have white horse, we can have black horse, we can have brown horse, and so on and so forth. So it is impossible that in any set of n horses, then all horses will be of the same color. But let's see what happens if we try to use mathematical induction. Now, the statement of obviously is true when n is equal to 1 because with one horse, it must be of the same color. Now, assume that Pn is true, so that in any set of n horses, then all of them are of the same color. And we want to show that Pn plus 1 will be true based on Pn is true. Now, we now have n plus 1 horse to begin with, and we want to show that they are of the same color. So how can we do so? So first of all, from n plus 1 horse, we can take away 1 so that we have n horses remaining. And because of the assumption that Pn is true, then we know that after we take out one horse, all the remaining horses are of the same color. And what is next? Next, we are going to put back the removed horse and then take away another horse instead. Now this time, after we put this back and take away another one, the resulting group will also have n horses only. And because Pn is true, then the resulting n horses must be of the same color. So originally n horses are of the same color, and then after that n horses are of the same color, and then we take out one, take in one. So in that case, they are all of the same color. So now, if Pn is true, then Pn plus 1 is true. So by the principle of mathematical induction, then all n horses in any case will be of the same color. So if you understand what is going wrong, that's great. If not, then think about this. And then, yeah, if you still do not know, then check up the OCW recording. The previous induction technique is the basic form. We usually call it the weak induction. There is another form called the strong induction. Strong induction shows two slightly different arguments. So the first one is nearly the same, actually exactly the same. We show that Pn is true for some base case n is equal to k. But for the other statement, we call it the inductive case actually. We show that Pn plus 1 is true based on much more information. We base on the fact that pk plus 1 up to Pn, they are all true. So here, what it means is that because we are now assuming that pk plus 1 up to Pn, they are all true, and use this assumption to show that Pn plus 1 is true, then that means that this is much easier to show because we make a stronger assumption here, a stronger assumption of what is already known to be true, and show that the next step is true. So that's why we call it a strong induction. So strong induction makes a stronger assumption, but it turns out that because we have more to assume, then that means that it is easier to show the resulting result. Now, why this method works, it is also very easy to understand. Because from the first statement here, we know that pk is true. So because pk is true, so we know that pk plus 1 is true. Now we know that both pk and pk plus 1, they are already true, so we can imply pk plus 2 is true, and so on and so forth. So strong induction also works nicely. And perhaps there is some even stranger variant of induction technique. There's one called backward induction. Now in backward induction, the inductive case, which is like this, is the opposite direction. So instead of showing Pn plus 1 is true based on Pn, we are showing that Pn minus 1 is true based on Pn. So if I know that one certain case is true, then I know that the case before it will be true. And because we know that this is true, we know that the case further before it will be true, and so on and so forth. But to apply backward induction to show that Pn is true for all, let's say, positive integers n, then we need to somehow have a different types of base cases. We need to show that Pn is true for infinite number of base cases. Because that infinite number of base cases, so that means what? That means that if I want to show a certain case, let's say Pn prime is true, then we know that there are infinite cases to be true. So that means that there must be some case where we have P, let's say Pn, which is farther on the right side of n prime, to be true already. And starting from Pn, we can go backward one by one, and so on and so forth, and eventually we can reach Pn prime, so that we can show that for any value of n, it is going to be true. Okay, so there are actually examples that if we know backward induction, then it is much easier to show. Okay, we have two examples here. The first one is called the Josephus problem. So in this problem, we assume that there are n people, they are standing around a circle. So the people are labeled by 1, 2, 3 up to n, so there are n people around the circle. Now what we are going to do here is that we are going to eliminate every second remaining person until only one survives. So suppose that we have 6 people to begin with, so the people are like 1, 2, 3, 4, 5, 6 around the circle. So we are going to take out 2, because 2 is the second person now. And starting from 2, we will remove 4, and then we will remove 6. Now after the removal of 6, then what we will see will be 1 and then followed by 3. So we are going to remove 3. And after we remove 3, we will see 5 followed by 1. So we are going to remove 1. So after the removal in this order, 2, 4, 6, 3, 1, then we will see that there is only one people surviving, and it is person 5. And we want to have a quick method to calculate what is the surviving number. So if we start with n is equal to any general n, we use Jn to denote the label of the survivor. So what will be the value of Jn? Now, by doing some observation, you can try out all the cases from n is equal to 1, 2, 3 up to, let's say, 20. Then you will somehow see a certain pattern that you can deduce what is j of n for any n for the next value. And based on the observation, it is usually a good way to make an assumption that it is correct and try to prove it. It turns out that you can make the observation and then show that this observation is really true. So in particular, j of n is equal to some value, 2k plus 1, where k is the excess value of n from its closest to power. So for instance, let's say n is equal to 11, the closest to power smaller than it is equal to 8. So in that sense, j of 11 will be equal to 2 times 3 plus 1, which is equal to 7. Okay, let's take another example. So for instance, what is the value of j of 100? Okay, now if I want to compute j of 100, let us find out the closest to power less than or equal to 100. And then we find that it is equal to 64. So 100 is 36 away, in excess more than 64. And by this statement, we claim that j of 100 is equal to 2 times 36 plus 1, which is equal to 73. And why it is true? Then we can show this by induction. And then another example is the famous AM-GM inequality. So AM represents or stands for arithmetic mean. Arithmetic mean is we have a bunch of non-negative numbers, so they can be any non-negative numbers, could be real. Okay, so we can have n real numbers. Am, the arithmetic mean is we sum all of these n values up divided by n, so the average value in terms of the plus sign. So we add them all up divided by n. And the geometric mean is the average in the sense of multiply. So we multiply all of these a1, a2 up to an together and take the nth root. So the AMGM inequality says the arithmetic mean is always greater than or equal to the geometric mean. And equality holds exactly when all of these a1, a2 values, they are all the same. Now, in order to show this is true, the best way is, this is easy to show if I know that Pn is true. It is easy to show that Pn minus 1 is true. So it is a very natural case to apply backward induction. And it turns out that we can also show this when we restrict n to be 2 powers. So when n is a 2 power, then we can show it by induction that it is correct. And after that, we can show using logical substitution, we can show that Pn minus 1 is true if we know that Pn is true. So this is an example of backward induction. Okay, the next thing that we want to talk about is proof by contradiction. So this is also another very important technique. So when we review logic, we will see that if we have two logical statements, one is called P, the other is called Q, then P implies Q will be a new logical statement, right? And we find that P implies Q and not Q implies not P, they are logically equivalent. So we don't know whether P implies Q is true or false, but we know that no matter it is true or false, the truth value will be the same as not Q implies not P. And so in a lot of mathematical arguments, we will be proving statements in the form of P implies Q. For instance, if n squared is an even number and n is an integer, then n is even. So this could be a statement in the form of P implies Q. But sometimes, if we want to show P implies Q by assuming that P is true and then, hopefully, to get a result that Q is true, maybe this would be hard. Alternatively, one may also show this one instead, not Q implies not P. So for instance, in the previous example, we want to show if n squared is even and n is an integer, then n is an even number. So the other form, we call it the contrapositive form, is if n is not even, then n squared is not even. So we assume that n is an integer anyway. So we will always focus on the case that n is integer. So the first part says n squared is even implies n is even. The second part is n is not even implies n squared is not even. And it turns out that the latter statement is easier to show. And because this is true, then the original one will also be true. So this is called the method of indirect proof. And proof by contradiction is a special case of indirect proof. So in order to show a certain statement P is true actually is equivalent with T implies P, where T means always true. So P is true is equivalent to T implies P. And T implies P is also equivalent to, using the contrapositive, is equivalent to not P implies false. Something that is always false has a nickname. It is called a contradiction. So the proof by contradiction technique is we assume that not P is correct. So we assume that P is false originally, and then somehow we hope to derive at a conclusion that we have something nonsense. Okay? So this is a famous example that appears long time ago, maybe more than, I don't know how many years, maybe 2000 years more than. So in Euclid's Elements, the book Elements inside Euclid's textbook, okay? So we want to show that the square roots of 2 is irrational. So irrational means it is not a ratio between two integers. So 3 is rational. 3 itself is a rational number because 3 can be expressed as 3 divided by 1. And then 0.142857142857 blah 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 is also a rational number because it is equal to 1 over 7. And here we want to show that square root 2, no matter which two integers you are choosing, so square root 2 cannot be expressed as the ratio of two integers, let's say p and q. So square root 2 is not equal to any p over q for integer pq. So this is a very famous or standard example of showing how proof by contradiction works. I guess you have already known this in your undergraduate class, so take your time to rethink about the proof by yourself, and if it is not okay, then yeah, check up the OCW recording. Okay, and there are another example. So this is also appearing in Euclid's Elements. So we want to show that there are infinite number of primes. So prime is a number that has, prime is an integer, positive integer that has only 1 and itself as its divisor. An integer greater than 1, I should say. So 1 is not considered as a prime. Okay, so the first prime is 2, and then 3, and then 5, and then 7, and so on and so forth. And then we want to show that we will never run out of primes, so there are infinite number of them. A direct proof seems to be impossible. So unless we can have a formula that generates the next prime or generates a prime, but then so far there is no known formula that always works. Instead, we can show this by contradiction. So we assume that there are finitely many number of primes, and then we can derive a contradiction based on it. So again, yeah, think about this by yourself first, and then check up the OCW recording if you want to know the details. Another example is the pigeonhole principle. So this principle says if we have k plus 1 or more objects, and these objects, they need to be distributed into k boxes. Then no matter what happens, one of these boxes must have 2 or more objects. So to prove this is super easy, proof by contradiction. Yeah. So the contradiction here is we suppose that this is wrong. So what does that mean? So it means that even if we have k plus 1 or more objects, and even if we have k boxes, then there is a scenario that every box contains 1 or fewer objects. Okay, now this is something nonsense. The reason is that if every box contains 1 or fewer objects, then the total number of objects cannot be k. Cannot be k plus 1 or more. So in that case, we get a contradiction. Okay. And similarly, we have a generalized version of the pigeonhole principle. So this time we have n objects and k boxes. We want to show that one of the boxes must have at least the average taking the ceiling objects. So this notation means, I think we have talked about this in the tutorial. So the ceiling function is we take any real number and then find the closest integer that is greater than or equal to this real number. So the ceiling of 1.1 is 2, the ceiling of 4 is 4, the ceiling of minus 1.1 is minus 1, the ceiling of minus 7 is minus 7. Okay? And so originally we have n objects and we want to put it into k boxes. So on average, we have n over k objects into each box, but n over k may not be an integer. So in such a case, then we can claim that at least one of the boxes will have n over k taking the ceiling number of objects. Okay, now the pigeonhole principle, it is a very easily shown result, but then it can have a lot of amazing consequence. So a couple of interesting examples is here. So for instance, in a group of 6 people, where any pair will either be friends or enemies of each other, then we are claiming that we can find 3 persons such that they are having the same type of relationship. So we may be either finding 3 mutual friends or 3 mutual enemies, or friends or strangers here. Okay. You can also describe this using graphs. Okay. Assume that we have a complete graph with 6 vertices. So complete means that between any 2 vertices there is an edge. And we assume that the edges are colored. We need to find the colors for each edge. Okay, it can either be colored in red or blue. So it is going to be a colored complete graph where each edge is either colored in red or blue. Question 1 says, no matter what happens, we must be able to either find a red triangle or a blue triangle. Okay. The next question is, we want to show that there is a number of the form that consists of a decimal number. Okay, so in our usual standard decimal system, a decimal number of the form 111. So 111 means 111. 11 means 11. Okay, so there is a number of the form 111, and it is a multiple of 2009. Okay, so this note is created in year 2009. So I use that as an example. It can be perfect if we change this to this year. This year is 2021. So it is also true that there is a number of the form 111, which is a multiple of 2021. So this will work whenever this number doesn't have 2 or 5 as its factor. Okay, so we can solve this by using Pigeonhole principle plus some very fundamental theorem that you have already learned in your primary school. Okay. Now the third one says, so the third one is an extremely difficult example. It says that let us get a bunch of distinct numbers. So they can be real numbers or what? So, but they are distinct real numbers. We have n squared plus 1 of them. And let's make any arrangement of these n squared plus 1 numbers. We want to claim that no matter what happens, we must be able to find some of them inside. We can pick some of them inside, keeping the ordering in the sequence. So this is called the subsequence, such that after selection of n plus 1 numbers from these n squared plus 1 positions, the resulting is a monotone subsequence. So it is an increasing subsequence or a decreasing subsequence. Is that okay? This is extremely hard. And then actually, the proof that we are showing why this is correct is we are using Pigeonhole principle together with proof by contradiction at the same time. Okay, another example. This is also an this one is easy. Okay, so we want to show that in any 51 numbers from 1, 2, 3 up to 100, there must be one number that can divide another. Now notice that 51 is necessary to guarantee this to be true. If we have just 50 numbers, then it may be not true. So for instance, if we are picking the numbers, the largest 50 numbers, 50 numbers only, so we have 51, 52 up to 100, then we will see that nobody is dividing properly another number. So with just 50 numbers, it is possible that we can have none of these numbers dividing none of the other number. But on the other hand, in this question, we want to show that if we require one more number to be selected, so if we select 51 numbers, then no matter what happens, we must be able to find a certain number dividing properly another one. This is easy. Among all of these questions, I think question 2 and question 4, they are the easiest ones. Now the last one is a very difficult one. Yeah, because the last one, so usually when we want to apply Pigeonhole principle, usually we will need to know what are the pigeons and what are the holes, what are the objects and what are the boxes. Okay, and this question 5, it is hidden deeply. You don't know what should be the pigeons and what should be the holes. Okay, let me explain the question. So this question says, suppose we have a sequence of 30 positive integers, so maybe 113, 125, 111, something like this. But then the total sum of these integers is not far away from 30, it's just 45. We want to show that we can find a contiguous sequence inside this 30 positive integer sequence, a contiguous one. So need to be starting from one and then the next one and collecting all the contiguous ones, right? Such that the sum is exactly 14. Now notice that the hard part is exactly. In the original question here, the original information, we just know that there are 30 positive integers. We don't know the range of these integers. But somehow there is some hints. Because the total sum is only 45, we must know that a lot of them should be 1. Yeah, because if there are a lot of things greater than or equal to 2, then the sum is obviously much larger than 45. But even though we know that a lot of them is 1, it doesn't mean that there will be a contiguous sequence such that the sum is exactly 14. So this is something that is hard to imagine. So by a very tricky design of the pigeons and the host, then this one can be easily shown to be correct. Okay, now this is the end of what I want to discuss today, or hope you to have the progress for this week. And next time, we have also question 6. Yeah, question 6, I will leave it for you. But next time, we will talk about proof by construction. Okay? Okay, I think that's all for what I want to show. Okay, thanks so much. And really, thanks a lot for coming. Okay, and then see you next time on Tuesday. We will have the tutorial. And then next time, we will talk about maybe focusing on the solution of our latest homework. Okay, bye bye.